first part of this experiment, we determined the velocity minimum of the ball necessary to go in a loop one time. So to derive the equation, we set force integral equal to force weight. So that would be mv squared over r equals mg. So v squared equals rg. Alright, and the next step is v minimum equals the root of rg. That's the equation we use in class. And so we found the radius of the loop to be 0.11 meters, and gravity is obviously 9.8 meters per second squared. Okay, so the v minimum is the root of 0.11 times 9.8. And so the v minimum actually came out to be 1.038 meters per second. That's the speed needed to go around the loop one time. Over and out. So Vy equals VO sine this.
In the second part of our experiment, we're trying to determine the height needed to produce the minimum velocity as we did in part 1. To do this, we have to use energies. We use potential energy at the top of the top height that we're going to use. It has to be equal to the kinetic energy as kinetic rotational, so thus we include inertia and omega, plus the potential energy at the top of the loop. As we go through and derive our formula, we find that all the masses cancel, which leads to gravity times the height needed plus equals 7/10 of velocity squared plus gravity times the height of the loop we need. As we go through and plug in gravity and plug in known formulas such as 22 centimeters for the height of the loop and a minimum velocity of 1.038, we find that the height needed to produce a V minimum is 30 centimeters.
In this portion of the experiment, we're trying to find out VL, the launch velocity of the ball as it travels off the ramp. So we set up our energy equation. We have mgh equals 1/2 mvl squared plus 1/2 I omega squared plus mgh at the launch point. So we go down here, we look at the equation. All the m's are canceling out here, canceling out pretty good. Then here, the r squared cancels again. Then we go down here, we plug in the values. We have 9.8 times 0.3 equals 1/2 times VL squared plus 2/10 VL squared plus 9.8 times 0.21. Alright, then when we add all that together, we get 0.82 equals 12 over 10 VL squared. VL equals, of course, 0.857 meters per second. And that is tremendous.
Hunter, sit. Hunter, Hunter, sit. Hunter, shake. Hunter, shake. Hunter, shake. Hunter, shake. Hunter. I'm tremendousing him right now. Hunter, shake.
Hello. For part 4 of our experiment, we're going to look at an example here of a sort of setup that we have with a certain type of exposure. You could look at that and you could say, oh, I could see those. And then here, what we're trying to find is dx equals vt here with the periods, okay? dx equals dxt. T is time, okay? So we're going to try to solve for dx first, okay? That's here, and it's circled. And then it equals v naught cosine of theta, okay? That, of course, 0.857 cosine of 25 degrees equals 0.77 meters per second. And then you can kind of look at this problem number 37 from the 2007-8-9 grad night last year. Okay, then we can solve for time. And then here's time, okay? And then you set for time, you get Vy, okay? So Vy, you get V naught sine of theta, okay, minus GT. And like, we can't use 3 buses, okay? Okay, so here's 0.
let's set Vy to 0. Wait, sorry. Okay, here. Oh, wait. Okay. 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 All right, there. Okay, so Vy, we already went over that. We're going to set Vy to 0, okay? This is Vy. You have 0.857 sine 25 degrees. Okay, minus 9.8 t, because we're solving for t here. And then we're going to draw the loop. We're going to draw the loop. That's the loop. We're trying to find here, this area. Okay, the velocity. The time is 0.0575 seconds, okay? That we already solved. Okay, now we're going to go back up here, take dx, bring it down here to here, and then dx equals 6777 meters, 0.777 meters per second times 0.075 seconds, which is this, equals up here, okay, and then we get 0.058 meters, which is 5.8 centimeters, and we are finished with our experiment, and it was so tremendous!